Okay, so we've got that done. I need to pin myself. I always forget to do that. Okay. All righty. I want to start here at the beginning because there's a few things from last class that I wanted to say that didn't. So let me just quickly go through that before we start the rest of the presentation. First thing I wanted to do was to thank Mike Landum for his help handling the chat. We just launched right into that with Mike, and I didn't even introduce him. So that is Mike Landum, who is going to handle the chat questions for us. Many of you know Mike as being one of our instructors here in Cole for the bridge classes. So many of you are very familiar with Mike and what a great teacher he is. Not surprising that there were bridge people, in a math class, right? Another bridge teacher is here with us, Dwight Bowie, a good friend of mine. Dwight and I met each other many years ago in a Cole program. There was a history of math in the early Republic, early America, centered around the time of Thomas Jefferson. It was offered by one of the professors here at Keene State College way back in the day. Unfortunately, we don't have as much of that as we used to, where the actual regular faculty actually go ahead and teach a Cole course. That seems to be happening less and less. Back then, we had the wonderful experience of having one of the math professors teach that course, and that's how Dwight and I became friends. So that's the first thing, is to introduce and to thank Mike for that. The other thing I wanted to say was here in this slide here, I mentioned that in Euclid's Elements, he proves that the area of a circle is proportional to the radius squared, and mentions nothing about the constant of proportionality, actually how to compute the actual area given the numbers. This is not Euclid's concern anyway, but he does not mention the number pi at all. And I gave the impression he didn't know what pi was. That's the wrong impression. Not only did Euclid know that pi was about 3, but the Babylonians and the Egyptians 1,000 years before Euclid knew that pi was about 3, that this number that you can use, this ratio of the circumference to the diameter or the area to the radius squared, that number is about 3. The Babylonians and the Egyptians 1,000 years and more before Euclid knew it was about 3.1. They wouldn't have said it that way. They wouldn't have known what I meant by 3.1. They didn't have a decimal system yet, but their equivalent systems of fractions would amount to the same thing. So it's not that Euclid did not know what the number was. He had an approximation of it, long-standing, but it took until Archimedes to actually give us a way to compute what that number is, actually decimal point by decimal point, again being anachronistic and using the notion of decimal points. So that was one confusion I wanted to clear up. The other thing, oh yes, I'm sorry. In this slide here, I talked about our two central problems of the calculus being the tangent problem and the area problem. And I said that the tangent problem actually has an allied problem. And I implied that the area problem also has allied problems that go with it. I never got to that. I did want to mention that. If you remember, the problem aligned with the tangent problems are thought of or spoken of in the biz as max-min problems, extreme values of the curves, the highest value, the slowest value, the closest value of the curve approaches to a certain point, to a certain line, are examples of that. The area problem also has allied problems with it in a very similar nature. One is the length of the curve, called the arc length. The length of the curve turns out to be, to solve that problem, is very similar to finding the area under the curve. It doesn't seem like it may be the same, but in fact it is. Finding the center of gravity of a piece, either be a flat piece of a plane, a sheet of sheet metal, think of that, something flat and thin, or an actual volume itself, some kind of a physical volume like a pyramid or a cone, to find the center of gravity of that object where it would balance on a pin. Theoretically, it would be in perfect balance, is also an allied problem to the area problem. So the curve length problem and the center of gravity problem are also things allied with the area problem. And the Greeks knew this. The Greeks understood this idea, and it did broaden, the interest from a geometric point of view, just as geometers, which is what they were. Mathematicians primarily were geometers for, right up through the time of the scientific revolution. These broader problems did show the broader interest in these particular questions. Okay, so I think that's what I wanted to say. All right. Going through my notes, guys. I become more and more dependent upon my notes.
Peter, can you change your slide view so that it...
To do that right now, I left this up because I didn't want to go through all the individual machinations. Thank
you.
I'm now going to start the real presentation for the day, and we will go into slide view mode. Okay. So we had finished by defining the notion of a function, and I wanted to give you some examples of functions. Remember, a function is a rule, it's a computational rule, which if I give you an input value, the function will spit out a single unambiguous output value using some kind of a computational rule. Formulas, for example, our familiar formulas are all examples of functions. The area formula, pi r squared, is a perfect example of a function. You give me a radius and I'll compute for you an area. And mathematically, we would write that as the area is a function of the radius. The area depends upon the radius in this particular way, pi times that radius squared. We would say that the radius, the r number, is the independent variable. It's the variable you give me. Give me the radius of the circle, and I'll be able to compute for you the dependent variable, the area. Notice, of course, algebraically, I could go ahead and solve for the radius in terms of the area. The radius, therefore, would be the square root of the area over pi. Again, if you're not into solving equations, don't worry, just take my word for it, that if you were to solve the top equation, area is equal to pi times r squared, r turns out to be the square root.
That makes sense.
Yeah, we have a mute. I forgot one of my steps is to mute everybody. So let me go back and mute everyone. The only person who I don't want unmuted is Mike. So let me see if I can do that. We need to mute everyone. Okay, you are all now muted and you can unmute yourself proactively if you want to, but you are now by default muted. Okay, we don't want extraneous noise into the class. So if the area depends upon the radius, one can certainly write that the radius depends upon the area. Let me try that again. Okay, a little fighting with Zoom there for a minute, I apologize. So the radius will in turn depend upon the area, but notice we have a different kind of an equation here with the square root. We want to stay away from negative numbers under the square root sign. So in this function here, I wouldn't want to give a negative area, but of course I wouldn't, right? There's no such thing as the negative area of a circle. So the domain of this function is naturally restricted by the actual geometry of what we're talking about. Notice in the top function, there is no restriction. I can give any radius. I mean, even silly would be a negative radius, which I wouldn't do, but there's no natural restriction on giving a radius. Here in this relationship, and just noticing the idea of functions, that you do have to be careful as to what input values you give. It would make no geometric sense to give a negative a in that formula, although you certainly could, and you'd wind up with an imaginary number. It wouldn't be very meaningful geometrically, at least to us. As Mike, I think, pointed out last week, that functions actually are much broader than my definition. You can start with the fact that functions can take more than one input. Yes, as one extension of the idea of a function. And here, my example is the perimeter. To calculate the perimeter of a rectangle, you need both the width and the length. So here's an example of a function of two variables. I need to give two numbers in order to calculate the perimeter. And one would write that mathematically as that the perimeter is a function of the width and the length. Okay. Primarily, we will be staying with functions of just one independent variable. Okay. Here's one of our favorite formulas. Distance is equal to velocity times time. Capital D is equal to VT. Velocity, we can think of also as a fancy word for speed. We'll see the difference between velocity and speed at some point, but for right now, we can kind of think of them as just synonyms. We don't use S for speed. We use V for velocity because S we're going to be using for something else. Here's an important point about functions. Here we have the distance as a function of time, is the velocity times time. T would be the independent variable. The time, D would be the distance, would be the dependent variable. The distance depends upon the time. As the time changes, the distance changes. For example, in the study of uniform motion, where the speed is constant, V does not change throughout the discussion of a particular motion, then V is thought of as arbitrary but fixed for that particular discussion. So there will be a number of distance formulas. The distance could be 3 times t, or t over 7, or minus 2 times t. Yeah, there's no reason why you can't go backwards. As time goes on, you go further and further, below what place where you started, or to the left of where you started. There's no reason why physically that can't make sense. These would be all considered the same formula, the same function. Distance is equal to speed times time. Of course, they're different functions in the sense of they have different table of values, but what's different about them is just that parameter, okay? That parameter which specifies the actual velocity. Otherwise, the form of the function remains the same. This form of a function will become important to us. We will see families of functions because they have all the same form. They certainly differ in their parameters, and they differ therefore in their graphs and their table of values, and even in some of their properties. But if you stay within the same form, sometimes surprisingly, some of the properties of that family remains the same. They're properties of the family. And since the stuff that what calculus studies is functions, I wanted to make this point early on that we want to start to think about families of functions, and the way that's done is through the parameters that are used to describe the function. Okay. We now go into we now step a little bit deeper into our story. Remember, what I'm trying to do here, guys, as crazy as this may be, is I'm trying to give the complete overview of calculus, in one presentation, so that we see the whole picture, try to think about it, try to think about all the different ideas, and then see if during the rest of the course, we can sort some of this stuff out. This now is the other point of view. Remember, we have two different ways of looking at the problems of calculus. One is from a purely geometric point of view, okay? Talking about tangents and areas and all the rest. I said the other way in which to think about calculus, certainly in its initial stages, how traditionally it is taught, how traditionally where it came from, how it was developed by the mathematicians, the scientists of the scientific revolution. Through this other way was through the problem of motion. So I want to now introduce that point of view, look at it from that point of view, look at functions from that point of view, and then see if we can't see the connection between the two, between the geometric way of talking about these problems and the motion way of talking about these problems. This is profound stuff. This is deep stuff. This is not easy to absorb this. This will take a while. You will not get this all today. I'll try to introduce you to the idea that there is a connection and to begin to see maybe how the connection is made. Certainly, if you remember your calculus, you know this very, very well. This is really the heart of how calculus is taught, is to show the complementariness of these two ideas. I want to start this idea of looking at motion problems by first of all kind of grounding us in the role that functions play in this discussion, the problems of motion. Here's where the ideas and the notation and the concept of function really begins to play an important part. As long as we're staying with geometry, the idea of curves and equations for curves and analytic geometry is more than adequate. As a matter of fact, most of the mathematicians of the scientific revolution were geometrists, and they were very happy to stay in the language of curves. Well, they vaguely understood, of course, the idea of function, but they did not use it explicitly, and they didn't need to. Okay. One of the reasons why Newton and Leibniz are called the inventors of calculus, and we'll see in its history how there was so much more development done before Newton and Leibniz. But one reason why they are given the credit for inventing calculus is because they understood the importance of the concept of function and how truly this is what they were studying, and they were studying its properties. So let's look at the idea of function from this point of view of trying to describe motion. So here I have a ball is thrown straight up from the top of a cliff with a speed of 64 feet per second. And then the height of the ball is a function of time. Clearly the height will rise higher and higher and higher. It'll get slower and slower until it reaches the top. So we're talking more or less about this picture here than the second picture thrown straight up, but we're throwing it up here from the top of the cliff. So as the ball rises, the height of the ball depends upon the time. The height is a function of time. And take my word for this particular situation, the height is described by this function here. It's a mouthful. It's 80 plus 64t minus 16t squared. I give you that function. Please accept that for now. Clearly, it is a curve. Will have a graph. It will have a table of values. It will describe what the height is as the time changes. Let's look at this functional notation and let's see this translation process that we make of talking about something real, the motion of a ball as it rises and falls in the air, and this mathematical description of it as a function. This translation process is absolutely fundamental, certainly to all of mathematics, but particularly in trying to understand and get our hands around this mathematics of change, which is the calculus. Okay. We start with absolute fundamental, the table of values. As time goes on, the height will change, and we can compute these. We have a computational rule. Again, please take my word for it that we get out our calculator and put in different t's of 0, half, and 1, and 1.5, and keep putting those numbers in as t in this polynomial expression, and I generate this set of values. Okay. So I begin to ask questions about the real world, questions about the motion of the height of this ball. What height does it start with? What's its starting height? Well, what am I asking? I'm asking for the height when the time is 0. I can read that off of my graph, off of my table. Okay, at 0, the height is 80. What am I asking mathematically? I'm asking for f of 0. I'm asking for the number that goes with the time of 0. I would write that as f of 0. That's the starting height at the starting time. Are there any other times when the height is 80? Again, I can look through my graph, my table of values. Is there another place where the height is 80? Yeah, way down here at 4. At 4, we see that the height is 80. Well, that's an algebraic question. Is f of t equal to 80? at any other t? What are the t's in which f of t is 80? A translation from, does it have any other height of 80 to this algebraic expression? When does 80 plus 64t minus 16t squared equal 80? When does that happen? We have to solve an equation. Yeah, well, that's what Descartes and Fermat did. They went ahead and married geometry with algebra. They're able to answer geometric questions with algebraic translations and then algebraic solutions. Okay. Again, not concerned with you following the details of the algebraic solution. It's here in blue. For many of you, solving a quadratic equation like this by factoring and setting the factors equal to 0 is something that you know very, very well. Some of you have seen this maybe in freshman and sophomore year of high school, which was 1,000,000 years ago, and haven't seen it since. So please just take my word for it, that this is the algebraic solution of that question of when, for what t's do we get a computational value of 80? There's an algebraic way of answering that question. And there it is. There's the other solution at 4. When does it hit the ground? There's a real grounded question. How simple can you get? When does it hit the ground? What's the translation? What's the f of t that gives me 0? When is the height 0? That's when it hits the ground. This translation process is something which you have to learn. It doesn't come automatically. Some people find this translation process very easy, very natural. It occurs to them right away, this translation. For some people, this is very, very difficult. This is not the way they think. They don't immediately translate, when does it hit the ground, to this equation. No, this is not where they are. This is not how their minds work. They haven't been exposed to it very often, if at all. This is very much a different way of thinking. This requires time, experience to absorb this. Many people never do. They never spend enough time with mathematics to ever become comfortable with these kinds of translations back and forth. I ask you now just to appreciate them. That's all, not for you to be comfortable with them, not that you could have easily come up with this interpretation yourself, but to see, say, okay, I do see, yeah, I guess that's right, that when it hits the ground is when f of t is equal to 0. Yeah, I see it. I wouldn't have seen it unless you told me, but I see it. And since I have a computational rule for f of t, 80 plus 64t minus 16t squared, which I ask you to accept. Okay, I have not explained why it is. Just please accept it. That is the computational rule for the height of this ball. Then I've generated another algebraic question. Can I solve this equation? Not setting it equal to 80, but setting it equal to 0. And the algebraists with us will have no problem solving that equation. Okay, the techniques are exactly the same. I'm setting it equal to 0 instead of 80. The factoring handles a little bit differently, and I get different solutions. Notice one of my solutions is t is equal to 5, and there it is in the table of values. When t is 5, indeed, the computational rule gives us 0. You can appreciate the fact that if, if this rule was much more complicated, then clearly searching through the table of values is not going to be a very efficient way to answer these questions. One really needs the power of algebra to generate solutions like this, independent of whether the numbers are complex or not, whether the relationships with computational rules are complex or not. Hopefully, algebra will be able to grind this thing through if you need the algebra. You can't be searching through the table of values for these answers. It's not a very practical solution. Now, last question I'll throw out is if it hits the ground at t is equal to 5, if f of 5 is 0, we notice that f of 6 is minus 112. Well, that's what the computational rule gives. You put in the number 6 and you do that 80 plus 64t minus 16t squared. Yeah, that's 6 will give you a minus 36. I'm sorry, will give you a 36. And minus 16 times 36 is a big number. It'll turn that whole computational rule into a negative number. Turns out to be negative 112. It's a detail. Who cares what the number is? The point is it turns it into a negative number. Does it have any meaning at all? Okay. Does it have, certainly mathematically, it's true. It's on the function. It's in the table of values. Does it have any meaning in our context? Well, I think we can all agree, well, yeah, if there was a hole in the ground and the ball was allowed to proceed below the surface, that what that number would tell us is how far below the surface the ball would be after the first second when it reached that surface plane. If it continued to fall down, it would fall down another 112 feet in that very next second. Notice, by the way, how fast the ball is moving at that 5th second. It's moving very fast. Just in 1 second, it's moved 112 feet. Okay, that's quite impressive. Okay, if you look at 2 going to 3, here's the top of the motion at 2. Look how far it's fallen in just this second, from 144 to 128. Okay, not very far at all, right? About what, so 24 feet? This is 112 feet in the 5th second. Clearly, it's gaining speed greater and greater. Okay, so I wanted to show this translation process from asking real questions, turning them into algebraic questions, and then the fact that there is algebraic solutions available for those questions. And it's the function that is describing what's going on. And the functional notation is a very powerful one and a very useful one. Let me go through this one more slide here, and then I'll stop for questions. Same function, okay? Same situation. Here's our real picture. Here is the picture of someone from the roof, 80 feet high, throwing the ball up at 64 feet per second. And there's the trajectory of the ball. There's physically what the ball looks like in time, its path through space. Here's our table of values, same table of values, same function. But now I show you the graph. Okay. Remember, we have 3 different ways of thinking about this function. Actually, here there are 4. The first one, of course, is the function itself. 80 plus 64t minus 16t squared is the function, is the computational rule. The second way is the table of values that it generates. The third way is the first picture I showed you, the actual trajectory of what this function actually produces in the real world. It produces this picture. Hopefully, this is the correct picture of how the ball actually moves in space. And there's a fourth picture, and that's this graph. This graph is the same in one sense as the trajectory on the extreme left. This is a mathematical picture of this physical trajectory. And this, again, is a very difficult transition to make, guys. This is not something you do in one day. This is not something you even do comfortably in one course. You have to see this starting from 6th grade, over years and years and years of being introduced to graphs and curves and functions, become comfortable with seeing that what this is truly a picture of the ball in the air. It doesn't look like it. It looks like a parabola, for goodness sake. It looks like an arc. It looks like an arch. But yet I'm telling you that this is a picture of this straight up and straight down. Yes, because this axis here is the time. And as time goes on, as time flows to the right, this tracks the height of the ball. It starts here at 80 and goes higher and higher and higher until it reaches its top and then begins to fall lower and lower. It hits the ground at 5. Yeah, as we saw in our table, and it continues to go down to a negative 112 at 6. Yeah, the graph is perfectly happy with calculating the value at 6. It has no problem at all. In fact, it has no problem calculating the value at -1. The function has no problem with using all kinds of numbers in the domain. The question is, do they have physical meaning to us? Because now we're looking at applied mathematics, not just pure mathematics. This ability to have mathematics explain the real world, this ability for mathematics to move into its applied realm is is a difficult step for many people to make. You know the old saying about math course? Yeah, you know, I understood all the math, it was fine, but I couldn't do the problems. I couldn't do the word problems. I couldn't do the problems. I understood all the theory. I couldn't do the, you'll often hear that. People say, I kind of dropped that. It was because it was difficult for them to make that translation, that essential translation of seeing how the abstract math can be applied to something which is real. But I've only gotten started here with how much I'm going to ask you to go into the depth of this. Because if you can say with me that this graph here is a mathematical picture of this physical motion. Okay, this thing is called a position time graph. Very natural. It tells us what the position is. The height, here it is h, the position at any time. So it's called a position time graph. This here is actually the trajectory, okay? And they are the same picture. They're not the same picture physically. This physical picture is depicted this way mathematically. And now I just review for a second some of those questions that we had in the last slide. The starting height, f of 0, yes, right here. It's right here on the so-called y-axis. When the time is 0, here we're starting at 80. When does it return to 80? We could write that now, see that now as a geometric question. We can go straight across at 80, see where that line hits the curve again. That'll tell us that number 4. Here we translated when does it return to 80 to a geometric question, to a table of values question. I could solve that, make it into an algebraic question, translating upon translating upon translating the same question. When does it return to 80? Mathematics is the art of seeing the same thing in many different ways. I know I'm asking a lot. This is a lot of ideas at once. If you had the proper mathematical education, you have been seeing these ideas at least since 6th grade. But I know that that's a long, long time ago. Even if you have a proper mathematical education and you haven't seen this stuff in 30, 40 years, yeah, to be thrown at you all at once, I'm asking a lot. But we do have 6 more classes to go through this more slowly, okay? We do have more time. I do have more videos to show you. I do have more other people who have presented these ideas in very creative ways, better than me, better than I can present them. And I want you to watch the videos and see, again, another point of view of how these ideas are presented. I promise you, if you want to put in the time, these ideas will start to make sense, but not today, not all at once. You can't even expect it to be so. Okay, let me finish, because I'm not done with this slide yet. Okay, there's that algebraic equation again to answer the question when it goes back to 80. And now finally, I have a very different question. What's the maximum height? What's this place up here in the top of the trajectory? How high does the ball reach before it begins to start to fall? What is this point here, okay, at the top of the arch? What is the time? When does it reach its maximum height? This actually is not an algebraic question. This is a calculus question. This is that allied question I told you about the tangents. This is a classic question of that max min. Throughout the trajectory, when does it reach its highest point? If you think about that question, what I'm really asking is, at what time does it reach its highest point? Because if you can tell me the time, then I can easily compute the height. I can compute the height at any time, right? I have a computational rule. If you give me the good time, I'm done. How do I find the time of all those different times as it travels from time 0 to 1, 2, 3, 4, 5 seconds? What time does it reach its height? If I could only find that, I could answer your question as to what height it reached at that time. That's a calculus question to find that time. Yes, it's 2. Yeah, it's in the table of values. Clearly, if you look at all those numbers, 144 is the biggest number. You can see the symmetry of the numbers going on either side. There's a 140 on each side and a 128 on each side going forward. Yeah, that is the middle number. But again, this is not a very practical way of solving the problem by looking at the table of values. This is not going to get us very far once we move into any real functions with real numbers, real situations. We have to find other ways of doing this, okay, to find interesting questions like this. Yeah, so from a geometric point of view, it may seem very limited. You know, what's the highest point on a curve? How's it close to? But now this is much more interesting. Now, as we study the motion, my goodness, a very natural question would be, well, what's the highest point? I've thrown this thing up at a certain speed. It left my hand at 64 feet per second. How high does it go? What more natural question could we ask? What more interesting question would we like to know? What more practical question we'd like to know? How high up how fast do I have to throw it to get it up to a certain height if I want to, I don't know, hit something, for example? Yeah, these are very practical questions of the world. And it is calculus that's going to turn out to answer these questions. I'm not going to show you how they get answered today. I'm just trying to pose the questions, trying to pose the ideas that we want to think about. Last one, not finished with this slide yet. I asked you to think about the slope of the position time graph at different times. Here's this slope. I haven't even defined slope yet. We've only talked about it in a vague, kind of intuitive way. The slope is the, the slantiness of this line, how much it's rising. Its level of increase. That's what we mean by the slope. Here, there's an increasing slope. Notice that as we go further in time, the slope gets smaller, it gets lower, it gets less steep. Here at the top, the tangent line, not surprisingly, would be flat. Okay, and the slope, not surprising, if we had a formula, would be 0. And as we fall on the other side, as the ball begins to come down, the slope is now negative. And further in time, it seems to be more negative. I just ask you to agree with me that the slope seems to be tracking the speed of the ball. Just intuitively. I'm not saying it's exactly that, I can't make that, but it does seem to track it. It does seem that the ball is moving at a certain speed, this slope has a certain steepness, and then the ball is moving at a slower speed, it's slowing down until finally it reaches the top. It's no longer moving up, but it's not yet moving down. So its speed is 0. And then it begins to fall down faster and faster down. And so the slope, this purely geometric thing, seems to be at least tracking the speed of the ball in its trajectory. And we see it not in the trajectory picture, that we can't see that at all. Okay, we can't attach a speedometer to the ball, but we can see it here on this other mathematical picture, the picture of the position time graph, that we can see geometrically, perhaps something that relates to the speed of the ball. Even though this is a position time graph, we seem to have in some way captured its speed in some way by looking at the slope of the tangent lines. And this is the connection. This is the connection we need to make, that the slope of the tangent line is in fact the speed. This is why the two problems are aligned. This is why the scientists of the scientific revolution, who were primarily geometrists, and so interested in the problem of motion. This is why the greatest mathematical physicist probably of all time, Newton, invented the calculus, because this was his concern. His concern actually was not in pure geometry. His concern was in motion. And he saw this problem initially from a motion point of view. Of course, he knew the other interpretation, but this is where his investigations lie. This is how he discovered his version of the calculus. by these kinds of considerations. Okay, we've done a tremendous amount so far, and what have we done? 3 slides. Michael, can I ask you to unmute yourself and see what we say in terms of questions?
Yes, we had one comment, which I will echo, saying, I wish I was taught this way back in high school.
Thank you. Thank you.
And we have a couple of questions or observations. The question is, on this graph, if we photographed, if we took a video camera and photographed the ball itself, would we see that arc in this particular shape?
That's a very good question. If you were to string out the photos, if you were to lay one photo after the other, moving to the right, having a series of photographs and put them together, yes, you would see the height in the photograph. The ball would go higher and higher in the picture and then come lower and lower in the picture. And you would absolutely see that graph. Yes. That's a very good observation. Yes, excellent. Talk about translations. Wonderful.
And a follow-up, this arc doesn't factor in gravity, question mark. Haha. I think she's
I beg to differ. The reason why that ball is slowing down, the reason why that ball turns around and begins to fall down is because of gravity. If it wasn't for gravity, that ball would just go up forever. Oh no, this is very much dependent upon the law of gravity.
That's subtracting 16t squared, I thought was gravity.
There you go. There you go. The acceleration of gravity is 32 feet per second faster every second. And there's no coincidence that that 16 is half of 32. We will get into all this, guys. We will go through the great discoveries of the scientific revolution with Galileo and Newton to use our calculus. And we will see all this stuff again. Anybody want to unmute themselves and ask a question before we go on? Okay, let me go on to the probably most important slide of the presentation. This, I guess, would be the central slide. And for all of those you have taken calculus, you know what's coming. You know this picture. I don't care if it was 40 years ago. You still remember this picture. Okay, we have a curve, and we trying to find the tangent line. Actually, because we're working in analytic geometry, because we're working in X and Y, because we have a function, because we have a particular value X of 0, because we know its functional value Y0, F of X0, as we would write that, because we have all this structure, I actually don't even need to know the tangent line. What I need to know is the slope of the tangent line. Because once you tell me the slope, I got the line. I know the point is X0, Y0. I can tell you what the line is. The line is Y minus Y0 is equal to M times X minus X0. Duh, that's the line. The only number I don't know is M. That's the number I need to find in analytic geometry. Oh, the Greeks, they had to do all kinds of constructions to actually physically find the line. We've gone way beyond that. Descartes and Fermat has brought us to a totally different level. We just need to find a computational way of finding M given that number X0 for this particular function. Question is, how do we do that? How do we find the M so I can fill in the equation of my line, and then I can make my table of values and I can draw my line and I'm all done. How do I find that line, this tangent line here? Well, one way to do it, and I'm being facetious, so come around to this again, is I could take a point Q1, near P, and I could draw a line from P to Q1 and ask, well, what's the slope of that line? And it would be, some slope. For Q1, we'll call it M1. Maybe it's about time we define what the slope is. Yeah, it's come to that point. We cannot proceed without now knowing what the slope is. No, I'm sorry. I take my change in X from P to Q1. How far do I go over in X to get to Q1? And I see how high up Q1 is from P. How much higher is Q1 from P? What is the change in Y as I go from P to Q1? As I go over in the X value to Q1, how high do I go up in Y in Q1? That's the slope. That's how it's defined. It's defined as the change in Y over the change in X. Okay, that's a definition. It's just a number, guys. It's one number over another. It's a fraction. Okay. What does a fraction mean? It's the ratio of how much change in Y do I have for every change in X. And that particular line, this line from P to Q1, has a certain change from here to here. If I were to take a shorter change in X, only up to here, I would go to Q2 and I would get a different line. And I would have a different change in Y for a different change in X. I would get a different change in Y. And in fact, the ratio would be lower. Right? This slope is lower than this one. It's less steep. Same formula, but my change in Y over my change in X is different. I could take a closer point, have a smaller change in X, get a comparably smaller change in Y for this particular graph, because it's a rising graph, and the less change in X I give it, the less change in Y the computational rule can muster. I will get the slope of this line. I think you'll agree with me that just intuitively, just visually, that as Q gets closer and closer to P, as I go from Q1 to Q2 to Q3 to Q4, as I get closer and closer to P, that the slopes of the lines PQ get closer and closer to the slope of the tangent line. Why would that be? Well, because the lines are getting closer and closer to the tangent line. So therefore the slopes must be getting closer and closer to the tangent lines. Why do I say that the lines are getting closer and closer? Well, visually we can see that. But more importantly, what is the tangent line? Is the tangent line is the line that only touches the curve at one point. And we can see that Q2 is kind of a better approximation than Q1, because although they do touch at 2 points, they touch at a closer point. And Q3 is even better because between P and Q3, they touch the curve at the 2 closer points. And Q4, they touch at even a closer point, and I let Q4 slide closer and closer and closer. And so that line, although it is still touching the curve at 2 points, are touching at closer and close. So we're getting to be more and more like it's touching just at 1 point, which is what the tangent line is defined to be. So yes, the slopes of those lines would be getting closer and closer to the slope of the tangent line if we can agree that the lines themselves are getting closer and closer to the tangent line itself. I said facetiously that this is one way of finding the slope of the tangent line. I'm here to tell you guys it's the only way. Oh, I can take any line and calculate its slope. I can go ahead and draw any line through P and say, that looks pretty good. Looks like it only touches the line in the curve in one place. Let me go out in space, pick another point way out there, let's say by the T of tangent, pick a point out there and do this calculation, the change in Y, the change in X with that particular line. I'll get myself a slope. No problem calculating the slope of a line. How do I know that's the right line? How do I know that's the tangent line? How do I know that? I only have 1 point. I just have the point P. How do I find the slope of a line when I only have 1 point? I need 2 points to calculate a slope. The only way I, in fact, can find the tangent line is by approximating it like this. And by looking at the pattern, if there is one, of seeing how these slopes begin to approach closer and closer the number that I'm actually looking for. And we have a piece of notation for this. That the change in Y of the change in X as the change in X gets smaller and smaller. This is a very nice notation. It has a formal meaning, but we're not going to worry about that today. All this is what it looks like. I'm trying to find this set of values, change in y over change in x as they change. I'm trying to find the change in y and the change in x as I keep making the change in x smaller and smaller and smaller. I claim from this intuitive geometric argument that that number, as delta x gets smaller and smaller, would be getting closer and closer to the tangent line. And so I say the slope of the tangent line is the change in y over the change in x as delta x goes to 0, if there is a pattern. And of course there will be. There will be a pattern. We'll see it today. Well, okay, I seem to have solved the problem, at least geometrically. I now know how to find the slope of the tangent line. I go ahead and take these series of points, let them get closer and closer. I can use a very nice mathematical formula. You could imagine I could take initial delta x and then cut it in half and cut it in half and cut it in half. I could do all kinds of things. I could make a geometric progression like Archimedes. I could find a way to shrink delta x in a very regular way and see if there's a pattern. And that's what we'll do. And it solves the problem. Okay. So let's take a look at that. If a picture's worth 1,000 words, right, then a moving picture is worth 2,000 words. Hello. Okay, we have our favorite function here, x squared. And I've drawn a small piece of it from 0 up to just about 2. And I've got this point here, a half. Okay, and here is the values. This caption thing is blocking, unfortunately, but for a half, this number here is a quarter. The computation rule is squared. The square of a half is a quarter. So here's my point, a half, a quarter. And I'm taking another point, 1 away, from a half to 1.5. This is my change in x of 1. I go from a half to 1.5. The black line goes with the black number. This is a change of 1. I claim that my change in y is 2. I'm going from a quarter up to 2.25. Again, trust me on these numbers. Okay? So the change in the length of the red line is 2. The slope of this line here is 2 over 1. It's just a number. It's a fraction. It's 2 over 1 is 2. Now, if I were to change to a different number, if I were to come down, not to a change of 1, but only a change of 0.9, or let's be a bit more dramatic, to a 0.8, now my change is 0.8. Now my change is not a full 2. It's only 1.4. But the ratio has also changed. Now, instead of having 2 over 1, I have 1.44 over 0.8, which is only a ratio of 1.8. So the whole slope has changed as I get closer and closer. Look at the slope. It's going down to 1.7 and 1.6. Oh yes, my change in x is changing. I'm going from 0.5 to 0.4 to 0.3. And as I change that, I compute the new change in y, and I compute the new slope, and the slopes are in fact changing. I program this down to a 0.1. Here's the lowest I went, 0.1. I think we can see the slope seems to be getting closer and closer to 1. Do you remember what the slope was when we did this back last Friday? I said the slope was 2 times a, 2x. Well, yeah, well, if the a is a half, then 2 times a half is 1. So, yeah, I was right. The slope is 2 times 1. Okay. I could take one more. I could go down to 0. Yeah, and it breaks. Mathematica breaks. I get indeterminate. It's not this. This is not the problem. It's this. I have 0 in the denominator. You can't have 0 in the denominator. Mathematica doesn't know what to do with that. Okay? I can't go all the way down to 0. I can only take 2 points. I need some other points. as close as it might be. Now I could take a different point, go up to a simple point. Let's go up to the point 1. Can I go up to point 1? Yes, here we are at point 1. And now I have my change of 1. And now I go from 1 to 4. Okay, because here's out at 2, 2 squared is 4. So my change of 1 gives me a change of y of 4. I go from 1 to 4, which is a change of 3. And so the slope here is 3 over 1, which is 3. And as I change, get closer and closer, as I go down to a change of just 0.8, now I have a change of just 2.24. And so my ratio of change is 2.8. And that 2.8 will get lower and lower. You can see the slope. Look at the line. The line is getting less and less steep. It's getting flatter and flatter. Okay, this is as far as I go. Notice that the number seems to be getting closer and closer to 2. Well, the number here, x is 1. And so I did say that the slope of the tangent line was 2 times whatever that number was. Seems to be right. So this is the purely geometric answer. Okay, this seems to work. Okay, I need to do a lot of work on this. I need to see if I can find patterns. But that's okay. Mathematics is the science of patterns. As a mathematician, I'm very happy to study these patterns to see if I can come up with some algorithms that will generate easy ways to compute this trend line from my patterns. We have a lot of work to do, but it seems like I have the fundamental idea here. I just need to be able to get out my mathematical instincts to see if I can find some patterns here. This is the purely geometric problem. What about the real problem? What about that problem of motion? Well, look at this graph once more, guys. And let's let x be time. And let's let y be height. What you're looking at here, or let y, I'm sorry, let height maybe is not the best. Let y simply be distance. And let this be the position of rolling down an inclined plane. Okay? We will start at the top of the plane. We'll call that place 0. And as time goes on, it rolls further and further and further down the plane. And what did I claim that this tangent line is? I claimed it was the speed of the ball as it rolls down the plane. Well, isn't that what these slopes are? As we go back to these different slopes, in this amount of time, the ball has gone from this place on the plane to this place on the plane. It's gone further down the plane. What have I found here? I found the average speed. In this amount of time, in, I don't know, 0.3 seconds, it's moved, I don't know, 1.2 inches. It's gone 1.2 inches per 0.3 seconds. That's a speed. I could, write that in a nicer way, talk about some number of inches per second or per 2 seconds. The ratio is not going to change. Okay, I can make it easier to our ears, but basically I'm finding a ratio of how far I've gone down the plane in an amount of time. And as I look at shorter and shorter times, what I'm finding is the average speed at a closer and closer place in the trip as it moves down the plane. I'm finding an average speed at a shorter and shorter interval. What does the tangent line represent? It would be the actual speed. The line exists, it's here. If I only knew exactly what it was, well, the pattern can tell me. The pattern will tell me what this is, because the algebra can't help me. The only thing that can help me is the form, is the process, is the pattern that I can discover. We won't discover that pattern today, but I'm telling you, can you see in your mind's eye, there could be one here. We could have a chance at finding a pattern. Okay. So let me finish this most important slide. So what have I argued? I've argued that if this was a position time graph, and as we saw this as free fall, truly this is a graph of free fall, or moving down an inclined plane at a slower rate. It's getting faster and faster and faster. It's rising faster and faster. What these slopes what these changes of y over change in x is now the change in position over the change in time. This is the average rate of change of f of x position with respect to x time. That WRT is a math thing. It's with respect to, okay? Saves real estate. So what this delta y over delta x is something real if the graph is something real. If we move from pure mathematics to applied mathematics, all of a sudden delta y over delta x is delta distance over delta time. It's the change in position. It's how far I've traveled in a certain amount of time. It's the average speed during that time. It's the average rate of change of the distance with respect to time. And this is an average in a shorter interval of time. And this is an average in a yet shorter interval of time. And if we've agreed that these numbers are getting closer and closer to the slope of the tangent line, then what is the tangent line? What is the slope of the tangent line? It's the instantaneous rate of change of the curve at that point. That's a real philosophical problem. It's the instantaneous rate of change at a point. Is the curve changing at a point? I understand it changes at 2 points. It goes from one point to another. You're telling me it's changing at a point? Well, is the ball moving at an instant? It's the same problem. Is the ball moving at an instant, or is it, I don't know, is it stationary? Yeah. The Greeks saw this problem. Yeah, and they tackled it. We'll tackle it next week when we get to our next presentation. These are among the areas, things called Xenos Paradoxes. This is a fiction. This is a fiction, what we have done here. In the real world, we have made this up. We have said that the instantaneous speed, the speed right at that instant is going to be the process, where the process takes us. Wherever the pattern takes us, we're going to call this the instantaneous speed. Well, we can call it whatever we like, but is it going to work? Will it work in the real world? Well, that will be the proof in the pudding. Okay, Newton will show us that it works in spades. Okay, he will solve the system of the universe using these ideas. These do work, but right now, yeah, it looks like it, but okay. So the instantaneous change is one point. How do I find it? Only by looking at the pattern among points which are close to it. It's the only way to do it. That's the process of calculus. And the rate of change is the heart of the matter. The rate of change is what calculus is about. It is what calculus is about. It's actually not about tangents. It's not about areas. It's not about speeds. It's not about any of those things in particular. And what functions are the things that calculus studies. But what actually it's about is the rate of change of functions. That's a mouthful. That's about as abstract as you're going to get. That's about it. That's the most abstract sentence you're going to hear all day. Trust me, maybe all year. This is very, very difficult stuff. Very difficult stuff. So please watch the videos that I show you, because this is other people better than me explaining this stuff in a different way. You really do have to hear this more than once. You have to hear it many, many times. You have to try to live with this. You can see why solving problems is helpful. Trying to get your hands dirty with the math will help if the initial presentation can make sense. It's difficult stuff. And before we leave this slide, I just want to look at this one more time. The change in y over the change in x as delta x gets smaller and smaller. This is a wonderful piece of notation, and we will formalize this to mean something. This kind of embodies the process. This embodies the pattern that we're looking for. We just don't know yet how we're going to try to find those patterns. Okay, so what the tangent line, the slope of the tangent line is, the slope is the instantaneous rate of change of y with respect to x. All right, I think if we can get through this next slide, this is the second most important slide. That was the most important slide. This is the second most important slide. Can we actually define the derivative? That's what we've been leading up to. Okay. So let's take our favorite function with table of values, and let's take a point A. Remember that I already claimed that we answered this question, that the equation of the tangent line, I know exactly what it looks like. It has this form. Talk about forms to equations. Yeah, this is a very important form to the equation. The parameters are a squared, and m. Okay, that defines a whole family of straight lines. In fact, it defines every straight line you can think of, except for vertical lines, technicality. And in fact, we solved this problem. If you remember, I said that m was actually 2a. You give me an x and it's simply 2x. That is the answer, it turns out. When we find the patterns, we will discover that. We will actually prove this particular example in our pattern search. And there's our tangent line. So what have we discovered? We discovered that the slope m depends upon x, right? You give me an x, I'll tell you a slope. You give me an x of 1, I'll tell you the slope is 2. You give me a slope, an x of 2, I'll tell you the slope is 4. You give me a slope, you give me an x of 0 down here at the vertex, I'll give you a slope of 0. 2 times 0 is 0. You give me a negative number over here, and I'll give you 2 times a negative number, which is a negative number. And yes, the slope is definitely negative. It's going down. It's a very nice function. This 2x is golden. It tells me what the slope is at any point on this curve. It doesn't just work for the number 1. It doesn't just work for this place A. It works for any place. A is a parameter. A stands for any value of x. So the slope is itself a function of x, just as y, the curve itself, is a function of x. It has a computational rule, x squared. The slope has a computational rule. In this particular function, it's 2x. So m is a function of x. We'll call it s of x for slope. Okay. It's defined to be, that's what the 3 bars mean. Okay, it's not equal to, it's actually defined to be the end process, the end of this pattern search, that it's defined to be all those other slopes as delta x gets smaller and smaller. That's a pattern search. We have to understand this and study this. All I ask you to do is see it in your mind's eye, and it turns out that that computational rule is 2x. So s of x is 2x. Nice rule. Remember what the pattern is? I take any 2 points, my point P and some other point kind of close, and I let delta x get smaller and smaller, and delta y gets, and I look for the pattern. That's what this bunch of symbols means. Shrinking down this triangle. Has a name, it's called the differential triangle. Okay, and this is what Leibniz used to discover his calculus. We'll see all this. It's a function. The slope is a function. It has a name. It's called the derivative. That's all it is. That's what the derivative is. It's derived from the original function, x squared. Okay, that's where it comes from. So this s function is derived from the f function, and it's called the derivative of f. It has its own table of values. For every single number x, I simply double it. Very easy table of values. And the slope at 5 is 10. And you can see, imagine if I go way out at 5, imagine how steep the parabola gets. Very steep. Yeah, the slope will be 10. Okay, so it's a perfectly nice function in itself, and certainly s depends upon f. Clearly, if I had a different parabola here, if I had a different kind of curve, if I had a sine curve or an exponential curve, certainly the derivative function would be different. So certainly the derivative function depends upon the function f. It must come for that in my pattern search. So the notation that we use, calculus uses notation of f prime of x. Very natural, kind of, I have f, well, this is f prime. It's a notation. It reminds us that the derivative function comes from the function f. So we give it a hit, we give it a prime. The other notation is Leibniz notation dy dx. Where does that come from? It comes from the delta y and the delta x. This is that when you shrink down delta x to 0, just before 0, I don't know. We'll have to see what Xenos Paradoxes say about this business of trying to find a change when there's no change. But the way Leibniz tried to describe it was by changing the deltas to a d, and said, well, it's that smallest possible change you can imagine. Use that change to find the slope. That'll be your slope of your tangent line. What's the smallest change? No, it's not going to be a smallest change, although Leibniz was perfectly happy thinking that way. No, we will eventually find a better way. We'll, the pattern will tell us something a bit more, but that's what the dy dx means. It's trying to get after that as delta x goes to 0. And so this is the derivative function. It's derived from the original function. What you spend 90% of your time on in Calc 1 is learning the rules of how to go from f to f prime, and how to solve problems, how to find the highest value and the lowest value and the steepest value. You spend 90% of your time learning those rules and solving those problems using those rules. And so little time is spent on what we have spent 2 classes on. And we've only spent 2 classes. If you're in Calc 1, you deserve much more than 2 classes on this, because this is the heart of the matter. But they kind of rush through this and they start slinging derivatives around. Okay, we're not going to do that. That's pointless. Okay, that's not what I want to do here. That's not what you want. Okay, I don't want. We don't need more rules in our life. The rules have to mean something. We have to know why we want these rules. It would be nice to know how high that ball goes. It would be very nice to know if I can give you that trajectory. If somehow or other I could hand you that trajectory function, it would be nice to know how high that ball goes given its initial speed. If I knew the force of the ball. From the force, could I calculate the initial speed? From the initial speed, could I calculate how high it goes? Therefore, from the force, could I calculate how high it goes? Can I calibrate different forces to different heights? Can I analyze the motion, the mathematics of change? Yeah, so that's what we're trying to do here. Okay, I have given you a lot. If it's at all possible, I have given you more ideas in this class than I did in the first class. All right, let me get out of this. I'll hold this. And Mike, we have, if we're not all exhausted, are there any questions?
There was a question about that first slide on
This one here?
Yes, finding the slope of the tangent, and it's just asking, when was this developed? What was the state of math, the history of, the historical context, I guess?
Well, of course, I'll ask you to hold on that question, because this is what we'll be doing. I mean, we will be doing the history of calculus. This is the whole point of our class, is to try to understand calculus in its historic settings. So I will be answering that question at length. I may be giving you more information than you want to know by the time we get to our last class in late April.
And the only other question was, I took the liberty of answering, was that triangle symbol, delta. Does that mean change? And exactly, that's what it means.
Yes, I'm sorry. See, this gets back to Antonia's thing about vocabulary. I am so used to this vocabulary, it doesn't occur to me. I have to remember, as a teacher, you have to remember so many things about what I assume that people know that they don't know. Yeah, the delta symbol is a universal symbol in mathematics and in science for a change. When you see delta, Z, that means we're talking about a change. Z goes from one value to another, and delta Z is the difference. It's actually Z2 minus Z1. It's the difference between the Z's. It's how much Z has changed to get from Z1 to Z2. It's called the change in Z, and it's symbolized as delta Z. I don't even remember that I don't remember. I don't even remember that I never knew that. That I never not knew that. So thank you, Mike. That's you need, you guys who are, obviously Mike is much more familiar with mathematics than many of us are, and so he is a great sounding board to try to fill in what I'm neglecting to fill in. Needs to be filled in that I'm neglecting to fill in. So I very much appreciate that. Anybody want to open their mic and ask a question?
I'd like to see if, this is Antonia, I'd like to see if my understanding of why this is all important is, I think I had a little revelation. So Jackie Bradley's in the outfield and he's throwing a ball in and he's trying to hit the guy at second base so that he can be, get the runner out. And Jackie Bradley is intuitively knowing that the trajectory of that ball, it's not going to be a straight line to the second baseman. He's got to figure out where the second baseman's arm is going to go.
Antonia, Antonia, you stick with this course. You're a gem.
And so
please,
if he stays,
do not drop out of this course. You are doing well.
So it's not, he doesn't need calculus for that.
Yeah, what he needs, he needs two things, Antonia. He needs tremendous amount of experience. He needs to be throwing thousands and thousands of balls since he's 6 years old, and he needs talent. He needs those.
But if you're in Houston and you're trying to throw a payload to reach the guys at the space station, you need calculus to calculate that trajectory.
Because we don't have any experience in doing that kind of stuff, although experience does help as time goes on to correct our mistakes so that we can correct our programs, which do the calculations. And this is wonderful metaphor. Just thank you so much, Antonia, for this.
Thank you.
I really think, let's capture in a real way, these ideas. Anyone else have anything to contribute, question-wise, comment-wise, whatever? Anyone have any other thoughts before we go?
Hey, Peter, it's Mike. It's interesting. Your two lectures bring back the tragic memories of my difficulties understanding calculus in my later high school and college years. And until I started practicing as an engineer and then teaching physics related courses. And of course, calculus ends up being one of the major factors in all of that work. But it wasn't until I saw the top-down applications of real-world problems that I began to appreciate the bottom-up development that you're presenting. I'll use one. I'll use one. We all believe in the conservation of energy because the universe wouldn't be here without it. But when we apply the conservation of energy to real world problems right in front of us, we find that the equations no longer are simple functions, but in some cases they are discontinuous and not describable as simple algebraic functions. And so we use numerical solutions to.
You're going a little bit deep into the weeds for most of the class. So I appreciate what your initial remarks, but you're going a little bit too deep for us at least at this point. Those engineers, they'll do that. Listen, I don't want to keep you guys any longer. If you have other questions, hold them. We will start next Thursday's class with other observations of where we've gone so far, okay? I hope you're not disappointed that it's taking more than 2 classes to go through the first presentation. I don't know how to rush this without just, well, I could run through this stupid thing in a half hour and it wouldn't mean anything to anybody, not even to me. So hold on to your questions. We will come back to this, but I do want to let you go. All right, guys, have a good week and see you next Thursday.